Thank you for coming to the first PhySU Prof Talk of the year, hosted by Professor Braverman. Professor Braverman actually did his undergrad here at U of T, where he worked with Professor Steinberg, Professor Julian, Professor Stuyvesant, and quite a few others. Afterwards, he did his PhD at MIT and then did a postdoc with Robert Boyd at Ottawa. And if you're in quantum optics, you definitely know the name Boyd, so it comes from quite a lineage. And so today, now he's a professor doing experimental quantum optics here at U of T, and he's going to be telling us a little bit today about quantum optics as a whole, as well as specifically laser cooling. So without further ado, thank you.
Thank you so much for a nice introduction. And thank you everyone for coming on Friday evening instead of going to party and doing your homework. You could be doing your homework here, I guess. All right, so I will draw a line. I will draw some numbers on it. I may need more space, but we'll pretend. Okay, so where are we on this scale? Right now we're somewhere here. Right. So we all know that room temperature is not 300 Kelvin, but when we're doing our physics homework, we always say it is because it's close enough. All right, what's the hottest that it's ever been on the Earth? Outside of like human-caused conditions or fires, just like ambient conditions. Yeah, so as far as I know, the hottest temperature ever recorded on the surface of the Earth was like 60 degrees Celsius, so 340 Kelvin. That's somewhere here. Okay, and what's the coldest temperature we've ever had on the surface of the Earth? So 270 Kelvin is around 0 Celsius. So. Aha, that's right. So about minus 90 degrees Celsius in some very cold part of Antarctica. They once measured that. So on this scale, that'll be somewhere here. Doesn't really matter if we're off by a few degrees. Okay. Does anyone know how cold liquid nitrogen is? It's used to make delicious ice cream. That's right. So liquid nitrogen is here, 77 Kelvin. How about liquid helium? Yeah, 4 Kelvin. That's right. Should be about here. All right. What about the surface of the sun? That's pretty hot, right? I'm going to stop writing the zeros because it's going to get impractical. Yeah, so something like 6,000 Kelvin, right? And then the cosmic microwave background radiation, which is if you just point your telescope at nothing and look, that's something like 2.7 Kelvin. Okay, and what if you have a very, very hot star, like one of these like blue giants? How hot is the surface of that? Something like 20, 30,000 Kelvin. Okay, can anyone think of even hotter things than the surface of a blue giant? What is the temperature at the center of the sun? That's pretty hot, right? Gonna need a few more orders of magnitude for that. 10 to the 5, 10 to the 6, 10 to the 7. So the center of the sun turns out to be about 15 million degrees. Okay, and then I had to dig into this for a while, but eventually I found out the temperature of a supernova. Does anyone know the temperature of a supernova when it explodes? I mean, it took me quite a bit of searching. So, and I don't think there's a definitive answer because a lot of it is based on modeling. Okay, so it's between a 10 and 100 billion Kelvin. Okay, and then the hottest temperature that, as far as we know, has ever existed in the universe since the Big Bang is at the LHC. They make these quark gluon plasmas. is about here. Okay, so 5 terakelvin, which is astronomically large. Okay, so compared to room temperature, how much hotter is 5 terakelvin compared to 300 Kelvin? How many orders of magnitude? That's right, about 11 orders, 10 orders of magnitude, right? About 10 orders of magnitude. Okay, so what I'm going to tell you today is that in the basement of this building, there are places which are as cold compared to this room you're in as a quark gluon plasma in LHC, but colder by that amount. So now we have to draw the lines going down here. All right, so other phenomena you might see at 1 Kelvin. I thought I would run out of space, but I didn't think it would be quite this bad. Right, so this is 1 microkelvin. So the coldest kind of bulk object that anyone can create can also be found in the basement of this building in devices called dilution refrigerators. Which basically uses a mixture of helium-3 and helium-4 to get down to about 10 millikelvin. And so anything below that can only be achieved so far with basically dilute gases of atoms and molecules that are laser cooled inside of a vacuum. So here. And so again, just to give you a sense of scale, kind of a basic laser cooling experiment will put you in this range. So typical laser cooling. Laser cooling with basically certain kinds of optical transitions which have narrower line widths will get you to kind of this microkelvin range. And if you want to get even colder than that, for example, to make what are called Bose-Einstein condensates or degenerate Fermi gases, you have to do some extra steps. For example, the most common approach is what's called evaporative cooling, which is like cooling your cup of coffee. You remove the hottest atoms, and the remaining ones get cooled down. So down here, it's evaporative cooling. Okay, so I also had to look up the number for what the coldest temperature is. I do not remember it off the top of my head. So I think, so one thing to keep in mind is all of this stuff is very small numbers of particles, and it's only existing in a kind of transient manner, right? Because if you have a bunch of atoms in a vacuum chamber, they don't really want to be sitting there, right? They want to fall down to the bottom and get stuck to the wall. They're much happier stuck to the wall. So you're kind of transiently cooling them. But the record temperature is 10 picokelvin. So how many orders of magnitude is that? Let's see, 2, so 13 orders of magnitude on this side. So it's ironic that it's actually much, well, I don't know if it's easier, but it seems easier to cool things than to get them hot. That's kind of as the introduction. Any questions? All right, so maybe now you want to find out why someone would want to make things this cold, right? And basically, the motivation at the end of the day is to be able to probe, control, manipulate, and study the properties of these individual atoms in an environment where they're very well isolated from the universe, and therefore their properties can be determined very accurately. So, control and measurement. All systems, of course, obey the laws of quantum mechanics, right? But in order for us to be able to observe them directly, these systems have to be isolated. And these ultra-cold atoms, ions, and molecules sitting in a vacuum chamber are basically the most isolated objects that we have been able to create as a species, and therefore they allow us to make the best quantum experiments. Kind of at the end of the day, what you want to do. And to understand why you might need to do this, what's the kind of typical speed at which the molecules of air travel in this room? Just order of magnitude. That's right. Right? And so if you cool it down by a factor of 1,000,000, then the speed now becomes 0.1 meters per second. Means that you have 1,000 times longer to do any kind of experiment that you want. A typical experiment might have a volume of a couple of millimeters. So at the ballistic temperatures of that you have at room temperature, you might only have a few microseconds to do your experiment. Whereas once you laser cool things, the atoms or molecules or anything else will sit around for much longer, and you can trap them. Yes? You can, please. Just give me 1 second. I mean, the basic approach is really quite simple. So it's a small diversion, but I think it's still part of the overall narrative. So evaporative cooling. So you make a trap for your atoms whose potential looks kind of like this, kind of like a Gaussian function. And then you have the atoms sitting around in here. They don't have to, you don't have to think about any of their quantum mechanical properties. You can just think of these as like balls bouncing around in a bag, basically, right? And you can kind of draw the maximum energy that they have. But of course, we know that when you have a bunch of particles bouncing around, sometimes they'll have more than average kinetic energy. Other times they'll have less than average kinetic energy. And so if you have a condition kind of like this, where the average kinetic energy is, say, half of the amount of energy it takes to escape, then sometimes one of these particles will have enough energy to fall out of the trap and never come back again, right? And you notice that this particle takes more than the average amount of energy. So the average temperature of the remaining atoms goes down. And so, of course, as you evaporate, you notice that the temperature gets colder and the process slows down, right? Because if you were down here, basically there would be very little probability that any of these would have enough energy to escape. But what you can do is you gradually make the trap less and less deep. So this way you can get the atoms to cool down. And so this process is actually remarkably efficient. I don't remember the name of the term, but basically when you lose a factor of 10 in the number of particles, you can make them colder by like 1,000 to 10,000 times, just by taking advantage of the fact that you remove so much more than average energy particle. Yeah, so by making them cold, you can study them for a long time, and you can trap them, which lets you study them for even longer. All right, so now I guess I should tell you about how we do this. So laser cooling relies on an effect called optical molasses. And you'll see why it's called molasses in a moment. But the key thing to remember is that molasses are viscous. And if you try to jump into a vat of molasses, you kind of get frozen in place, right? All right, who here has heard of the Doppler effect? All right, great. Just checking. All right, so the setup is very simple. So you have your atom, and this also works for molecules and ions and stuff. I'll just always say the word atom, so but interpret it more broadly. And as you probably know, atoms have quantum states. Yes, you know that atoms have quantum states. Okay, good. All right, so you have some ground state and excited state. Don't be scared by the notation. I will not use it. Okay, so there's some energy difference between the ground state and excited state. Great. The other thing you need to know is that excited atoms tend to decay back to the ground state. And the way this happens is that you shine some light onto the atom, and the atoms can absorb some photons and can emit some photons. So you have scattering. You have Doppler shift. Okay. So now what you do is you take a laser and you make two laser beams out of the same laser, coming in from different directions and hitting the atom. Sure. And you choose the frequency of this laser to be slightly lower than the transition energy for the atom. Your energy, this would be something like this. So E laser. Choose omega laser to be less than the resonance frequency of the atom. Okay. So then the other thing you have to know is that the atom has resonances, but these resonances are not infinitely narrow, right? So there's some wiggle room in what laser frequency you choose that the atom will still scatter. And if you plot the scattering rate as a function of laser frequency minus atomic frequency, you have a curve that kind of looks like this. The width, we label it by gamma. This is the line width of this transition. And it's also equal to how fast the atom will decay from the excited state to the ground state. Okay, so now let's go back to our atom. What happens when the atom is stationary? When the atom is stationary, remember we chose our detuning to be negative. So let's say this is our laser frequency. Atomic frequency, like this. You have two laser beams. They both have the same frequency. They come in from opposite directions. The atom will sometimes absorb light from one of them. Sometimes it will absorb light from the other laser beam. And the probability is equal. And then the other thing you have to remember is that photons carry momentum. So every time the atom absorbs a photon, it gets a little kick. But because the rate at which it's absorbing the photons from both lasers is the same, the kicks average out, and then you don't get any net force. So that's for a stationary atom. So what happens if the atom is moving? Some speed, which is not zero. Okay, so in this case, the problem is actually kind of difficult to do if you're in the lab reference frame, but it gets much easier if you go into the reference frame of the atom. Right? So we kind of boost ourselves into the reference frame of the atom, and in the atom's reference frame, what happens to the frequency of this laser? It's blue shifted. Right? And then this one, of course, gets red shifted. Which, when we go back to our picture here, the blue shifted laser is now closer to resonance than before, which increases its scattering rate. The red detuned laser, the red shifted laser, sorry, is even further from resonance than before, and the scattering rate goes down. And what this means is that there's a net force going to the left. So this is for an atom moving to the right. I think you can easily imagine that for an atom moving to the left, the opposite argument holds, and you get a force that will push it to the right. So at the end of the day, you get a force that's some negative coefficient times the velocity. So this is a damping force. And that's why it was called molasses, because it doesn't matter which way you try to move, you get slowed down. Questions about molasses? A lot of people shaking their head sideways. Yes. Yes, you would get heating. So usually you will detune by kind of a line width. So this is usually gamma over 2 in the kind of mathematically ideal case. And you of course need to know what the typical line widths are. So for alkali atoms like rubidium or potassium, which are very common in laser cooling, this is 6 megahertz. And to give you a sense of scale, the laser frequencies, which correspond to optical frequencies, are usually on the order of 400 terahertz. So these are actually quite narrow resonances, right? Like if you calculate the Q factor of this resonance, it's like 10 to the 8. You know, and this is considered a broad transition. This is actually a pretty wide resonance. There's much narrower ones. Is there another question? Gamma is, it does several things. It's the width of the resonance. So basically, if you have just this atom sitting there, and you have your laser, and you have a knob that tunes the frequency of the laser, and you observe how much light the atom is scattering, it's the width of the feature that you see. So as you scan the laser frequency, you see no scattering, no scattering, no scattering, and it goes up, and it goes down. And so the width, in terms of how much you've tuned the laser, is gamma. But also, if you are able to prepare an excited atom, 1 over gamma is how long it will stay excited before it decays. This is not a coincidence. There's a fundamental reason why these are related. Yes? Absolutely. That's right. So the reason why we like to study atoms with these techniques is because atoms have a small number of resonances, and these resonances are very narrow. And so you can very specifically address particular transitions, right? Obviously, real atoms are not just 2 levels. You have many different levels, right? But in atoms, it's not that many, and they're all narrow enough that you can actually pick out, by choosing the laser frequency, to only drive a specific transition. You know, when you have a number of atoms like in this desk, the number of resonances is approximately equal to the number of particles, and then they kind of all get densified and clumped together. Right, so there's many different kinds of laser technologies, but at the end of the day, all lasers have 2 basic parts. They have a cavity. The cavity is just 2 mirrors that let light bounce around. And then you need what's called a gain medium. Then the gain medium is basically a material you can pump energy into that will experience stimulated emission when the light bounces around. I'm happy to tell you more, but I think it will take too long. You can ask me after. Any other questions? Yes. Aha, very good question. So I'm glad you brought this up. So there's actually a related question, which is what happens to the entropy of the particle, right? Because, you know, to cool things down, as you know, if you've taken StatMech, that entropy has to be dissipated, right? Okay, so the energy is in some ways easier to understand, right? So the energy goes into, so you absorb this photon. So, and remember, we're in the moving reference frame. In the moving reference frame, you scatter more of these than of those, and then you re-emit the photons in some random direction, right? And so if we go back to the lab reference frame, you will find that these photons, on average, have a higher frequency than the photon that you absorbed. So it's basically you can think of the atom as a mirror, right? And I don't know if you've worked through this problem, but if you have a source of light and a mirror moving toward the source of light, the reflected light will actually be blue shifted. And so the same thing happens with the atom. When the atom scatters the photons, they leave with a slightly higher energy than when they came in. No, of course. Absolutely. So the density that you can achieve is limited by this rescattering process. And there's all sorts of tricks for getting around it. The most common one is basically to hide the cold atoms. So once the atoms are cold, you do something to them to basically make them go into not one of these two states where they basically don't interact. So they stay cold, and then you cool more atoms. So the second question about entropy. The place where the entropy goes is that this light comes in a well-defined spatial mode. That's not important. It also comes in with a well-defined frequency. Right? You can think of the spectrum of the laser as a kind of temperature. And when the light is rescattered by the atom, it comes out with a broadened spectrum, because depending on which way the photon is scattered, it will be blue shifted by a different amount. So you broaden the spectrum of the light, and as a result, entropy is generated in outgoing light. That's where the entropy goes. Okay. Fortunately, I don't know enough about cosmic microwave background or cosmology to answer that question intelligently, but I would love to learn more. Yeah, so you might want to trap them in some other method. For example, you could trap them magnetically or optically with another that doesn't scatter as much. Okay, so, and I guess I didn't want to speak for too long because I wanted to leave time for other kinds of questions, also show you a few nice pictures. So I just want to add one more idea, which is that optical molasses will cool the atoms, but it won't trap them, right? Because the atom might get stopped, but it doesn't really care if it stops here, or here, or here, or here. And for all of the fun quantum experiments that we want to do, we need like a reasonably dense collection of atoms so we can actually like grab some of them and do some experiments. To do trapping, we use a technique called the magneto-optical trap. That's a little bit more involved as far as atomic physics goes, but I'll try to make it comprehensible. Okay, so there I had this kind of two-level abstract atom that only had two levels. Now we have to introduce a little bit more quantum levels. So the bare minimum you need to trap atoms with this technique is 4 levels. You still have your ground state. Now you have 3 excited states. And I draw this diagram in a suggestive way because this is some measure of the angular momentum of the atom. So you know that in the ground state, your electron is orbiting the nucleus. In the excited state, it might be orbiting with more angular momentum. And quantum mechanics, once you have a non-zero amount of angular momentum, you can basically think of it as spinning in different directions. So you can think of this state as the electron spinning one way, this one as the electron spinning the other way, and this state is some quantum mechanical thing where it spins in both directions at the same time, but on average it doesn't spin. That's the basic idea. And so what you do is you still have your atom, you still have your 2 laser beams, but now you want to use the polarization degree of freedom of your light. And so what you make for these laser beams is you make them circularly polarized. Circular polarization just means that the electric field of the light, instead of oscillating linearly, as you might have seen, kind of goes in a circle. So you kind of get the idea that this light also has angular momentum. It's spinning. And if it spins one way versus the other way, it turns out that, and so this one is also right-handed circular. So basically, the right-handed light can only interact with this transition. And the left-handed light can only interact with that transition. Okay? So here, when all of these levels have the same energy, and then again, as before, you detune your laser from resonance, same way as there. And so right now, everything is the same as before. right? The scattering rate of this laser is equal to that laser. The force is the same, things cancel out. If the atom starts moving, then you still have the Doppler effect, and you will still get the cooling effect. Okay, but where does the trapping come from? And the trapping comes from making a magnetic quadrupole called an anti-Helmholtz coil. And an anti-Helmholtz coil is a device which has two coils where the current runs in opposite directions. If you calculate the magnetic field, it will look something like this. So basically the field kind of points inward along this direction, and then it points radially outward. And you go along these horizontal directions. And you notice that there's a 0 in the magnetic field right in the center, and the magnitude of the field increases as you go away. And so what the magnetic field does is it induces what's called the Zeeman shift. The Zeeman shift is a shifting of the energy levels of the atom that depend on the size of the magnetic field. Basically, you can think of the electron spinning around the nucleus as being a tiny little magnet, and so depending on if you're spinning along the external magnetic field versus opposite to the magnetic field, you get more energy or less energy. And so what it does in this picture, let me just draw it in a slightly more exaggerated way, that's easier to see. So this is 0 magnetic field. And if you have some non-zero magnetic field, we'll get something like this, where the energy of this state is shifted up, energy of that state is shifted down. So what you can see is that now this laser is closer to this resonance and will scatter more photons. This laser is further from resonance and will scatter fewer photons. And so as you go away from the center here, one of these will start scattering more and will exert a bigger force on the atom and push it back to the center. So this is how magneto-optical trapping lets you trap atoms. Questions about this? It's crazy that it works. In fact, the magneto-optical trap is the very rare case of a phenomenon in physics which was proposed theoretically, implemented experimentally, and then it turned out that the experiment worked much better than the theory predicted, because this simple picture is actually, there's not many atoms that have this kind of level structure, and real atoms that people started laser cooling at the beginning, like the alkali atoms like sodium, potassium, and rubidium, have a much more complicated level structure which admits additional cooling mechanisms. And so they were doing these experiments and they were seeing that things were like 10 times colder than the theory predicted. And they were like, what is going on? So it took 10 years of theory to like really figure it out. And so there's something called sub-Doppler cooling, which happens in atoms that have a more complicated level structure than what I... Yes? These are very small magnetic fields. Yeah, like compared to magnetic fields that would actually trap a charged particle, they're actually quite small. Like, just to give you a sense of scale, kind of, you will form a cloud of atoms, and a typical size of a Mott cloud is about 0.1 to 1 millimeter. It's like a very typical size. It's actually quite a small object, and these magnetic fields have strengths that are, I guess, over this length scale would be like microtesla. Oh, that's because my drawing skills are poor. Well, because these correspond to basically the electron spinning one way versus spinning the other way. So it's like a magnet in an external magnetic field. Ah, how do we know how cold they are? That's right. We can't stick a thermometer in there, right? So yes, you can actually do that. If you have a narrow enough laser, you can actually measure basically the Doppler broadening. But typically what people do when things get very cold, actually the easiest thing to do is just to drop the magneto-optical trap, so turn off all your cooling lasers. And then the cloud falls under the influence of gravity, of course, but it also expands ballistically because the atoms have some distribution of velocity. So you measure how fast it gets bigger. Like, so you're literally watching it expand. Remember I told you it was about kind of 10 centimeters per second? So you drop it for a few milliseconds, it expands by some fraction of a millimeter, and you can actually see it get bigger. Depends on how long, how many particles you want to trap, like how good your vacuum you have in your system. But typical time for making a MOT is anywhere between 0.1 and 1 second. Kind of the typical duration of this kind of cooling procedure, and then you will trap, depending again on the species you're using, between 10 to the 6 and 10 to the 9 atoms. Kind of the typical numbers. Yes. Okay. So ions are kind of special. So optical molasses works exactly the same for ions. For trapping ions, you have extra techniques because the ions are electrically charged. And so there are things called ion traps, which basically use electrostatic forces to trap them. And ion traps are in many ways superior to the magneto-optical trap because you can get much deeper trapping potentials. And the other thing with ions is that, because they're charged, they repel each other. And they repel each other very strongly over large distances. So it's actually not possible to trap many of them at the same time. Kind of antisocial guys. Yes. You. Yeah. Did you not have your hand up? Then there's basically nothing to distinguish. Like there's nothing that creates an asymmetry between the forces acting from different directions as a function of position, right? Like the key point, the reason to have these multiple levels is it lets you use the magnetic field, which you can make spatially varying, to tell the atom where to go. Right? In some sense, the way you've set up these forces here is that the atom always wants to go to the place where there's zero magnetic field. And if you don't have multiple levels whose energies get shifted relative to each other, there's no way for the magnetic field to affect kind of the relative forces of different lasers. I mean, the atoms are constantly scattering light, right? So they're most of the time they're in this state, but then some fraction of the time they're in the excited state. Okay, so I have a few minutes to show you my one slide. The slide is because I can draw these things, but I can't reproduce figures from papers. I know my artistic skills are incredible, right? So as a result, I unfortunately have to resort to PowerPoint. Is it HDMI 1? It has a label. No, it's HDMI 2. Also a remote for the projector or something. Which projector would it be anyway? Oh, here, side projector. Aha, I heard a beep. Projector warming in progress. All right. Oh, do you guys have more? Oh, okay, perfect. All right, cool. That was pretty fast. Okay, so these are kind of, I'm going to skip over all of this stuff. Okay, so I'll just go through this. Is there a stick? MP always has a stick. Because I walked away. I'll just use my arm. Okay, so these are just pictures from a bunch of different papers, not necessarily the best papers or the only papers. They're just kind of good representative papers about different experiments using these kind of atomic quantum systems to do cool quantum stuff. So I'll just go through them. So on the bottom left, you have, maybe I'll use the cursor on my computer. That'll work better. I'm trying to wave enthusiastically. There we go. All right, so this is an optical cavity, and there's a microscope here, and you focus some light, and that lets you trap atoms in a localized way and also image them. So this is a picture of two atoms, individual atoms separated by 6 micrometers. And that in this experiment, they were basically using it to make a quantum network. So to interface photons traveling through one fiber to another fiber, basically switch which way they go, create entanglement between the atoms and the light. This is a picture of an ion trap. So inside of here, to your question, there's electrodes that trap the ions together, and then in one of the most common configurations of traps, you end up trapping a chain of ions. And because they repel each other, they're kept separate, but you notice that they're closer together in the center than at the edges, because in the middle there's kind of more ions piling up, and on the outside they're kind of getting pushed away by all of the other ions. This is a picture from what's called a quantum gas microscope. So here atoms were cooled and loaded into what's called an optical lattice. So using interfering laser beams, you can make an array of traps. So kind of a square grid of traps. And here you see, so the bright pixels essentially are individual atoms that are fluorescing, and if you're able to image, and these are used for doing essentially quantum simulations of materials, right? Because this is mimicking, in a material like a metal, you have a crystal lattice. So you have the nuclei, you have the electrons kind of fly around between the nuclei. And so here you have the atoms taking the role of electrons, and then the laser beams creating your traps taking the role of the crystal. This is a this is a electric field sensor that uses ultra-cold atoms, quantum memory, and then this is basically a quantum computer or a quantum processor. And let's see if I can get this little video to work. So this is a alas. So if the video worked, which it worked like 5 minutes ago because I put this video in here 5 minutes ago. 1 hour and 5 minutes ago, sorry. Basically what you would see is, so these dots are individual atoms again, and they would get moved around and kind of made to interact in different ways. And you generate entanglement, you do quantum gates, and then you can try to build a quantum computer. Okay, so any questions about these cool pictures? There's a million cool pictures I could show you, and I don't have enough time to show you all the cool pictures. So just to get you an idea that you can actually see single atoms, you can manipulate them, and you can use them for different things. Oh yeah, and of course in the middle is my favorite, which is to build clocks, but everyone has their own favorite thing to do. All right, so just to, I took about 2.5 times longer to tell you about the physics, and there's not enough questions, not enough time to answer all the questions I was expecting, but let me just tell you about how I came here. So I guess you already know all of this stuff. But here are some questions just to prepare the audience. Why did I do a PhD, and how did I choose what to do my PhD on? What did I do as an undergrad? Was it like being a postdoc or working in industry? So I spent 3 years in quantum computing startups. What was it like finding a job as a faculty member? Okay, other questions I came up with, I think these are good questions, but I can't answer all of them right now, but just to give you some ideas. So I think that's all I wanted to say. Thank you very much, and I'll take whatever questions you guys want.
Okay, thank you, Professor, for a very interesting talk. Do we have any other questions in the audience?
So subdoppler cooling is something that kind of happens on its own, and it happens when you have atoms that have additional level structure in the ground state. So for example, rubidium-87 is a very common isotope that people use for laser cooling. And so its ground state has 8 different quantum levels. And so the subdoppler cooling, there's a few different mechanisms again, and this comes about from quantum coherence being established between different ground states, or what's called optical pumping, which is different levels get populated by different amounts. So basically the atoms spend more time in some of these levels than some of the other levels. So you always want to make your things colder. There's just certain atoms that are more amenable to this phenomenon. Sorry, what makes what? Yes, exactly. So why do people, so to paraphrase the question, why do people like to laser cool alkali atoms or alkaline earth atoms? And that's because alkali atoms, from an atomic physics perspective, have 1 electron, so they're all kind of heavy hydrogen. And alkaline earth atoms essentially have 2 valence electrons, so they're kind of heavy helium. And so having fewer electrons is good because it makes the level diagram much simpler. And making the level diagram simpler is good because the thing I kind of glossed over here in this very simplified presentation is that for this whole thing to work, you need to scatter a lot of photons, right? Photons carry very little momentum. So to cool an atom from room temperature to basically standstill, you need to scatter something like 100,000 to 1,000,000 photons. And that means that if you don't just have two levels, but you have something like this, where you have these levels and then some other levels, and you're scattering light here, and the atom doesn't always decay back to the state you started with, but decays here, now you have to have extra lasers to get the atom back to this ground state. And so this is called a closed transition when it doesn't decay to other levels. And then these are called repump lasers. And basically you don't want to use too many lasers because lasers cost money. Yeah, so that's why. Yes? So it's to measure the temperature, right? So if they're hot, they move faster, and so they kind of expand. Yes, back there. Right. So on average, you shift the frequency by approximately a line width. And for optimal laser cooling performance, you're already about a line width below resonance. So these rescattered photons are kind of on resonance. But the main effect, even if you could cool, the main reason why the rescattered photons are bad is that they essentially cause repulsion between the atoms. Right? Because you have one atom and it scatters a photon, and then another atom absorbs it. Essentially, what this means is that between these two atoms, there is kind of a net transfer momentum that pushed them apart, right? And so that's what limits the density of your magneto-optical traps, for example. So if you look at some of these cool pictures I showed you, so basically, if you really want to confine atoms very, very tightly, you're going to use what's called an optical tweezer, which is you basically take a laser beam and you focus it with a microscope objective to be as tightly focused as possible. And that's what gives you stuff like this or like this. And here the atoms are localized to well below 1 micrometer. Fabricate. Right. I mean, the position control you achieve with these kind of techniques is actually not that good, right? Because the atoms are very cold, and at some level, you have to even start worrying about like the quantum uncertainty principle, right? When things are cold, there's very little uncertainty in their momentum, so there's more uncertainty in their position. Sure. So for like nanofabrication, people typically actually use very energetic particles. So like high energy ions or electrons to like mill out stuff from structure, from materials. And so those can be kind of a few nanometer resolution. But the other thing is that the amounts involved here are very, very, very small. Mm-hmm. The quantum clocks. Well, I mean, basically, if you want to build a clock that's kind of good in the modern landscape of performance, you have to measure the atoms for a long time, right? And so, how to say this? The sample that we study are these laser-cooled atoms, right? This is kind of the sample preparation step. In fact, it's often called sample preparation. Is when you have laser-cooled and trap them in a particular kind of trap, which is the thing that's shown on the top left there, and then you can interrogate them for a long time. Right. So, I mean, the kind of practical application of precision timekeeping is for things like navigation. GPS relies on very accurate clocks sitting on satellites to tell you where you are. But kind of fundamental physics applications, I don't know if it's really, but uses of very precise measurements is to test questions like, are the constants of nature constant? Right? So you probably know of constants like the speed of light, the mass of the electron. These are not real constants in the sense that they're just the ratio of meters per second, right? But some constants, like the fine structure constant, are dimensionless, or the ratio of the mass of the electron to the proton. And if those change, that's kind of a real fundamental change in the way the universe works. And basically, by comparing clocks, you could compare any kind of sensor, but clocks are the best sensor we have. And so if you have two clocks that operate on different principles, they will be sensitive to any kind of variations. So far, we have not found any variations in fundamental constants, but it would be pretty cool if we did.
I think we're running a little bit short on time, but if anyone has any other questions, maybe they can chat with Professor Braverman after. So I think let's give one more round of applause for our speaker today.